is very similar to shallow foundation. This is like a shallow foundation calculation. Okay? And here's the end bearing calculation. Okay? So today what we will do, we'll go through the theory, and one more extra thing in offshore applications is these steel piles. In offshore, you never use a concrete pile because it's very difficult to have a concrete pile there. So what I will do, I'll show you in a offshore application what are the problems there. Okay. Now, you remember that thing about this candle in the cake. What happens if you have a hollow tube? It's a candle, it's a solid, and a hollow tube. So putting it into the cake. What will happen? Where will we get the resistance from? In a candle, only outside, isn't it? But if you have a steel pipe, if you have a pipe, you get inside and outside. Yeah. So, if the pile drives with sort of inside, soil is coming inside, that means it is driving unplugged. It's not plugging at the bottom. It's unplugged, isn't it? In some cases, the soil can drive plugged. So the bottom is like a close-ended pipe. Okay? So in offshore, it's very difficult to understand which will go on. So therefore, what you do for offshore pile capacity, you work out two cases, called a plugged case and an unplugged case. Like an onshore, if it's a solid pile, you simply do the end bearing, right? In offshore, you take one case as sort of plugged. If it's a plugged case, so the calculation is you take the whole end bearing, right? So this would be QB. So you will take pi by 4d squared, where d is the diameter of the pile diameter, times end bearing resistance. You put down there, right? And end bearing resistance is something quite like bearing capacity, like CNC, half gamma NQ, gamma DQ and gamma, those terms. This is there, right? So this will have a unit of kilonewton per meter squared, kPa, and times meter squared, you will get this as a force. Okay? It's a plugged case, so bottom is plugged. And then what you do, you add here the friction part. So you add QS. So in this case, the capacity is QS plus QB. Now that's a plugged case. If you do unplugged case, if you do the same case unplugged, so that means so you have got here, so you have soil inside. Right? And here it is, so this thing is D, so here is annular, so you have got D outside, DO, and D inside diameter, right? So DO is outside diameter, DI is inside diameter. And know the wall thickness, yeah? So you can find out the outside inside. Now here the end bearing will be only in the annulus part. So therefore here the Q bearing would be pi by 4 d 0 squared minus d inside squared times Q B. Yeah? Only annulus part. But then you have here twice friction. QS also inside as well. So QS. So here the capacity becomes QS 2QS plus QD. So you find out two cases, plugged and unplugged. And you take the lower of the two, lower as your capacity. Yeah? There's a way to tell you, but okay, now you don't take risk. You don't take risk about, you know. Now can someone tell me what happens when you're having a pile, driving a pile? What happens? Which one would govern? Okay, so what happens? Say you hold the pile in that sleeve. You remember that jacket sleeve? You bang the hammer. So what happens? You bang the hammer. The stress waves pass through the pile, and that stress wave makes it to move down. So that vibration doesn't make it plug, because what it does, it sort of makes the soil and the pile add one another. So the pile completely drives unplugged. When you drive, it drives unplugged. So you put the pile in place, you leave it there for 6 months, because when you do the piling, you then start to bring the jacket, you put the thing there, you build it, it takes 6 months to build it. In those 6 months, the soil consolidates. When you apply the load, it behaves plugged. So when you drive, it drives like it acts like an unplugged. When it acts like a plugged. It's very complex. So when you drive it, you're driving with the soil getting in. Right? So when you drive the pile, because of the stress waves, you're banging a big hammer. Right? So you're not letting it, be like a plugged case. So it drives like unplugged. But once you finish the driving, it's stable, steady state, everything is normal. When you have the load, acts like a plug. Right? It's quite complex in a way how you do it, but in practice it's easy. You don't go for all these. You don't take risks. So, take the minimum.
It's very difficult to take account again.
But then you saw that hammer video. They're using vibro method to basically loosen the thing.
So stick with that.
Yeah. So there are ways that they can have a port cutter right now. They can develop technology. So once you can find out the forces, you can find the forces. How much is the forces? What are the stresses? You can easily work out a way to loosen these things up. Yeah. So in terms of capacity, so you work out those two things. And that's one of the first calculations you must do. That tells you how many piles you would need, minimum number of piles. So once you know the load on your foundation, then you choose the pile diameter, pile length. You then can find how many piles you would need. That's the first calculation you must do. You give the minimum number of piles you need. This gives the minimum number. You can have more than that. Yeah? Is there any question so far? Is there any question?
So QS, you have two QS. Which one is greater?
Well, because it's a very small wheel takes same. We normally don't do double calculations. So, but if you do Excel, you can do it, but probably for practical purpose, they're all same. The only small, diameter is a very small wall thickness. So we don't bother much about that. Yeah. Okay. Is there any question?
You essentially say that if it's unplugged, ignore the
The unplugged, you take the endless part. Endless part.
Yeah, what I'm saying is because the thickness is so small, can you not?
Yeah. So you
Can you not
take.
ignore it because it's so small in comparison to the shaft?
Because it at that depth.
It's still quite
Think of
considerable.
the bearing capacity at that depth. Quite big, isn't it? You look at the bearing capacity at that depth. It's quite. Yeah. Okay, so practically how you can do it, you can set up an Excel spreadsheet and you can make many layers, right? You can make many layers and then you can put down the soil properties here and start to estimate that. Now, how do you estimate all these things? It's important to understand the way how you calculate. So the bottom part, the end bearing is quite simple. So basically end bearing is area and the bearing pressure there, right? Now let us look back in this skin friction part. So in a skin friction, it is quite simple theory. So say for example, I've got a book, I've got can I borrow a book here? So I've got this book here, and I want to find out the friction. So the friction force is basically the more I react, so the more the normal load times the angular friction, isn't it? So more the force, more the normal force, more the friction. Yeah? So if you remember this, so you can easily calculate the friction. It's quite similar. So I am taking a small pile section. So taking a small pile section here at some depth. We can easily calculate at this middle of this depth, of this length, the sigma vertical stress. Sigma V dashed, right? So suppose I want to find out the friction in this part. It can be at any depth, right? So let's take the element N, nth element, right? I can calculate that, and then I can also calculate the lateral stress there and multiply by a K, which is the earth pressure coefficient, right? So if I know the vertical stress, I can know the lateral stress, okay? And then the friction would be if you are pushing it down, the friction will be opposing motion, isn't it? So you are applying, you're pushing it down from the top, so it wants to move in that direction, so the friction will be acting in upward direction. If you are pulling it up, upward direction. Yeah? Friction will always oppose the motion, right? So here is the friction. This would be, again, like the book problem, vertical. So here lateral force is this. So you convert this by K times sigma V dash times tan of delta, where delta is the angle of friction between the pile material and the soil around it. It depends on, it is a steel with sand, steel with clay, what type of, yeah? Now, what is the unit? Always remember to do units. It's very important. What is the unit there? So, K sigma V dashed times tan of delta. So K is unitless, lateral earth pressure coefficient, yeah? Sigma V dash is in kilopascal. This is no unit. So you get the unit of stress. And then the force will be what? Where is it acting? Everywhere, all around. So if this distance if this is, say, Z, this small element is Z, and the diameter is D, what is the area? Pi dz, right? Pi, so the surface area, so this area of the surface is pi d is the diameter, pi d is the circumference times z, the area. So the force, so the friction force will be pi times d times z times k sigma v dash tan of delta. Okay? So that's the whole theory. We normally take 1 meter element, so this would be 1. So you can easily, so you sum up for all the different depths, get the total shaft friction. Yeah? Then you add the end bearing part. Okay? It's important to make your mental model what we are doing. And otherwise, if you don't make the mental model, you will always remember, oh, I must do that, I must do this, then you might miss one. But if you see what we are doing, actually, we're trying to find out at what load you lose the pile. How can a pile get lost? When you fully mobilize the shaft and end bearing, you lose the pile. So how do you calculate? Calculate the whole friction and the end bearing. Plug, unplug, and do for both. And I add them up. Yeah? Yes.
Just to check, with the shaft friction, do you determine that at the midpoint of the layer for every meter?
Every meter, for that meter you do at the mid level.
Yeah, sure.
Yeah? But again, a code will tell you, and the code tells you all this stuff. These are varying from code to code. Now what I will show you is, like, if you use this code, what I gave you, an API code, they all are different. So what I have showed you is the theory. Now, so you can see how the code interprets that and gives the guidance. Yes.
So here we are taking the effective strength in the middle of the 1 meter.
Yes. So what you're doing, you are saying, I will have the, so that's the pile, right? So I said I will break it. I will break into element of 1 meter element, and then I say let's look into. So here's the pile. I take one element. For that element, let me find out the friction. So this is my element of 1 meter. What is the stress at the middle point? The vertical stress. What is the ground applying stress there? Then I find out what's the stress then coming onto the pile surface. So vertical stress times K will give you lateral stress. That's the stress there. And then the friction would be this times the friction coefficient.
But here, different from the shell foundation, the question that I have asked you before, that we took the effective strength and we did the clay, but then we told that this is wrong. So in
Oh,
that question,
that's how you calculate the vertical stress. That's a simple one. I will tell you there. There was one mistake in the calculation for that. But here it is here for any element you find out the vertical stress there. Suppose you want to find out how much is the friction for this part. This part. You find out the vertical stress here. Then you find out lateral stress. Then the friction. Right? That means you need that amount of force to mobilize fully the friction. Yeah?
So Z you take it as half, you divide by 2, Z?
No, the
whole
whole element, isn't it? The whole element. So whole element. So you want to find, first of all you want to know what is the shear stress there, the friction. So for the element, find out the vertical stress at that level. Then you find out what is the lateral stress. And then you find out the shear stress there. And that's shear stress. To get the force, you multiply the area, which is pi d times this. Yeah, and then you sum for all the forces. It's quite simple. So it is the lateral times the.
But if we have similar profile, the whole area.
Similar profile, it means that it's linear, isn't it? It's going by linearly. Then you take the whole dash because it's linear. So then you don't need to, because normally solids are layered. So in that case you cannot use it. Solid may have a different density at different depths. Then you have to add those. Yeah. Okay. Again, so I've here is the plug unplug. Yeah. You can calculate all these things. So there are ways to do it. So if you want to analyze, if you plug unplug, you got to then look into a figure diagram, do the whole calculation, and you can check. But this will take you nowhere, basically, because it's very uncertain. We cannot calculation take everything that happens in real field. In real field, you take a big hammer, you bang it down there. So if you use these things, it will give you to what depth it will plug, etc., etc. But perhaps it's not wise to do these things. It's good to do two extreme cases and take the lower as a capacity. Yeah. Okay. Now, what I will do, I will sort of today I will just go through the API code of practice, how to calculate all these things, and I've given you another approach. So once you do that, you also look into other approach. The main thing to show, actually, the theory is simple. The theory is you work out the friction and end bearing, but different codes will give you different ways to do it, right? Here is API, capacity for sand. What API is American Petroleum Institute code. It's one of the well-respected code. It is revised at least 21 times and is widely used in industry. And this now is ISO code. This became an ISO code. So, in this particular code, so what it gives you soil pile friction angle. That means it's giving you delta, right? And how do you calculate delta? It tells you delta would be 5 minus 5. Therefore, if it is sandy soil, your angle of friction is for the soil is 30 degree, you take delta as 25 degree. Okay? So if you see here, it tells you how to get that. So therefore, what it means that in this case, the angle of friction is 20 degree. So you take 5 degrees less. Okay. Then it tells you limiting friction value. Limiting. What that means? That means, so you can easily calculate K, sigma, Vds and tan delta. Right? That means if you keep on increasing the depth, sigma, Vds will keep on increasing. So suppose you get from this calculation, it is 55. You cannot take more than 47.8. So you said you cap at that value. Say for a particular layer, if you get more than this, you cannot take that. You take this limiting value. It caps a value to a certain level.
Is the limitation of the friction or from the sigma?
From the friction. So that's it says limiting friction. You see KPA. Look, always look in the unit. KPA. It's KPA, right? It's not giving you force. Because once you multiply area, you get the force. Yeah? Then, when you do end bearing, you need NQ. But again it says NQ for this soil. So if you know the soil, you know NQ, you take NQ and then you can work out your end bearing pressure, QB. So NQ times sigma V dash, but don't exceed more than this. It gives you a cap. That don't exceed higher than that. Okay? So what you do when you put down the calculation in Excel sheet, you have got a if clause, isn't it? If more than this, use this, isn't it? So you can code up in maximum. Maximum in okay. All right. And this is how you can do it, right? Okay, and then in terms of clay, that's for sand. In clay, what it does, it works out a strength ratio. So, suppose at a particular depth, you know sigma V dash, and you know the clay strength. So this is that ratio, SU by sigma V dash, right? And depending on that ratio, it tells you what to take as the shaft, sort of that stress value. So you can see here, it tells you to take here, and then so you can find out so this particular thing gives you the whole value here. Okay, and that's how you can calculate the skin friction. Here in this what I've also given you is also quite similar. So they give you also similar values there. So if you look into page 21, we see here it says alpha C. You see again that's the alpha C value here. Alpha C is basically that's the alpha value given here.
Can you find the graph that one? Can you find the graph that one?
Yeah. So this is for clay soil, the shaft resistance. Okay. Okay, so I'm now doing a pile in clay. Okay, so that's a small element. So at mid depth, I will work out sigma V dashed. And I know that this clay has the undrained strength of say 100 kilopascal. Okay? So I will work out SU by sigma V dashed. If it is more than 1, I come here, less than 1, I go there. I pick this graph, I get alpha. So I will get alpha is equal to sort of tau by SU. So then the friction for this part would be simply pi diameter Z times alpha SU. This is in kPa.
Which one do you read the midline or? Is that not?
These are actually measured data, and based on the measured data, the code gives you that line. To use this line. Yeah? Okay. So if you, yes, sir.
Sorry, Sylvie, could you just clarify, with that plot, like Sean was saying, do we have to use a line? Is there
Yeah,
a
so
three line process?
basically, the code gives you this equation.
So you use the equation rather
So
than-
the code gives you these two equations.
Sure.
In the exam, I also give you the equation.
So you use the equation rather than,
Okay, so I used to give equation as well,
yeah.
but in 1 year, there was a problem with photocopying minus became plus or plus became minus because the way how they photocopy, what I understand is that now I have to give graph. So easily, you can't go wrong. The equation, you see, is quite complicated because you have to have minus half, maybe to the equation, minus and minus 1 by 4, and minus becomes plus, it's a completely different number. If you graph, at least you know that, you know. So the equation is good if you are doing it in Excel. Graph is good if you're doing exam paper. You know that roughly, you know. Yeah?
Thank you.
Okay? If you have got still energy, you can start a tutorial problem. Or if you want, you can stop here today. I am working on your coursework. I am waiting for one document to come because you are buying some documents. So I will reduce the coursework in a way. What I will do, I will give you case studies from the previous years that students have done. I'll give you the answers as well. And I want you to reflect on that and write a short paragraph for those things. These have got a lot of learning value, those failure case studies. And I want you to go through those ones. I'll give you solved ones, read them, and make your own sort of inference. Yeah? And then the other one is that basement problem. Okay? Now I'm trying to do this because I'm giving you so basically, based on that,
Unfortunately, it's like 1.5 times longer than the bomb in the morning. You know, like last year. So, given that, I think it's longer than
We finish one this year.
Is this red?
We finish.
Yeah.
This one. I also think if you like, he's added like the design to see.
We finish
Steel and composite bridge
So
this week.
you now you deliver on what you're suffering.
Yeah, I'll go.
Probably